Continuity and end behavior is what we're looking at today. So, a graph is said to be continuous if there are no breaks or holes in the graph. Okay? So if you can start where the left arrow is, or the left point even if it is, and you can trace the graph without picking up your pencil at all, then it's going to be continuous. Okay? If there are breaks or holes in the graphs, if there are breaks and holes, it is considered to be discontinuous. So continuity, continuous, discontinuous, they're all different forms of the same word. So there are 3 types of discontinuity that we are going to talk about. So in this first graph, what do we know that graph has that we don't see? Asymptotes. There is a vertical asymptote right here at A, and there's a horizontal asymptote right here at 0. The horizontal asymptote does not affect continuity, but the vertical one definitely does, because if I'm tracing this, I have to pick up my pencil to go to the next part, so that's discontinuous, right? So this is called infinite discontinuity, because those asymptotes are infinite. So it says, when f of x increases or decreases infinitely as x approaches a. So as x gets closer and closer to this asymptote, it's going to decrease infinitely. Then that's what makes it an infinite discontinuity. Okay. So this next one looks like we maybe broke off a piece and pushed it up here. This one is called jump discontinuity. If it looks like you could take the 2 pieces of the graph and like snap them back together, that's going to be jump discontinuity. You have to be careful by saying, okay, well, I'm going to trace, and then from here I have to jump to get to this one. Because technically from here you jump to get to this one, and that's not jump discontinuity. Okay, it's like it's just separated apart from each other. You have to jump from one to the other. And so this says, when f of x jumps from one point to another, and that's what, so I am jumping from one point to another where I don't actually get to negative infinity or infinity, so you can look at it that way. And then I have this, where it's just literally a hole in the graph. This is called removable, because I just literally removed a point, or it's also called point discontinuity. I usually use the word point more, I guess, because there's a point missing, basically. So when f of x is continuous everywhere else except at one point, that makes it point discontinuity. Okay, easy enough? When you state discontinuity, you have to state the type, and then you also state the location. The location is not an ordered pair. The location is just an x value. Notice how it's saying at x equals a, at x equals a, at x equals a. It's whatever that x value is. Even though I could give an ordered pair for this, I can't give an ordered pair for this one or for this one, really, just that one. All right, so let's look at how this works. It says, determine if the function shown on the graph is continuous. If not, identify the type and location of discontinuity. So on number 1, is that continuous? No. So that is a no. So then I have to say, what type of discontinuity is that? Jump. So this is jump discontinuity. And it's at x equals what? 5, negative 5. Okay, we good? All right, look at number 2. Does it look like it's continuous? Yes, because I can trace the whole thing without picking my pencil, so that one's a yes. Number 3, does it look like it has any asymptotes? Yes, it does. There is an asymptote right about here. There's also a slant asymptote but that's completely irrelevant. It's only the vertical asymptotes that affect continuity. So this is continuous, and then it goes to here, and then I have this, so it's not continuous because there's two pieces. When it's an asymptote causing the problem, what kind is that? Infinite. Infinite. And that is at x equals 1, we'll say. Okay, we good on that so far? All right, I'm going to give you a minute. I want you to do 4, 5, and 6. Shoes are all squeaky today. I'm annoying myself. What do we think about number 4? Do you think it's continuous? Yes, because I can trace it. We're good. What about number 5? Is it continuous? No. Are there any asymptotes anywhere? No. Okay, I just have this hole, so I don't call it hole discontinuity. I call it what? Point. We'll just go with point. And that's at x equals -3. Yeah. All right, number 6. Is it continuous? No. Are there any asymptotes? Yes. I have a vertical one and I have a horizontal one. Right now, the horizontal one doesn't do anything for continuity. It's only the vertical one that affects it. Is that the only discontinuity I have? No. I also have a hole, right? So because I have a vertical asymptote, that discontinuity is called what? Infinite. And the infinite is at x equals 2, I think. I get too close. It's like a... And then the hole, we call it the what? Point. And that, even though it's so tempting to give an ordered pair, we don't. Is that at 4? Yeah, x equals 4. Okay, what questions you got? Anything? We're all good? Awesome. Let's look at in behavior. We're going to be talking about in behavior all year long, and it really is not that difficult. The only thing that, I don't like about in behavior, I guess, is that I've said so many times, when you're doing anything, you go left to right, bottom to top. But on part of in behavior, you do go right to left, but this is literally the only time you get to do that. Okay? So this says, as x moves towards positive infinity, so as x is moving towards positive infinity and negative infinity, in behavior describes what is happening to the value of f of x. So as x is going to positive or negative infinity, what is happening to y? Where is it going is what we're looking at. This is the key here, is that this is end behavior. We don't care about what's going on in the middle. We care about what's going on out at the ends, which usually we can't see because we're going to infinities. Okay? Don't care. The middle could be a hot mess, doesn't matter at all. So, when I look at this one, as x approaches infinity, that's how you read this, as x approaches infinity, so as x gets bigger and bigger and bigger, y is getting smaller and smaller and smaller, and y is approaching negative infinity. Do I need to say that again? Are we on the wrong slide, maybe? Then, and here's where we go right to left. It's the only time you get to do that. As x approaches negative infinity, so as x gets smaller and smaller and smaller, my y value is getting bigger and bigger and bigger, so y is approaching infinity. Okay? Does that make sense? All right. Like I said, it's really not that difficult, but you got to make sure that you remind yourself sometimes that you don't care about the middle behavior, you care about the end behavior. All right, so let's look at these next ones. I want to describe the end behavior of each graph. So when I look at this, first of all, what type of graph is this called? Do you know when you graph it? Okay, it might be a 90-degree angle. I was going to see if y'all knew. Because we're about to get into parent functions, and you got to know your parent functions. But anyway, we'll get there in a minute. As x gets bigger and bigger and bigger, so x is getting bigger, y is also getting bigger, so y is approaching infinity, right? As x approaches negative infinity, so as x gets smaller and smaller and smaller, what's happening to y? It's getting bigger and bigger and bigger, right? So it's approaching infinity on both sides because it's going up, up, okay? So then number 8. As x approaches infinity, what is f of x approaching? Negative infinity, very good. And as x approaches negative infinity, y is approaching negative infinity again. Okay. We okay with that? Okay. Now, on number 9, there's some asymptotes. I have an asymptote here, and I have an asymptote here. And if I had to guess, I'd say you probably haven't talked about slant asymptotes yet. That's okay. Just know that they exist. That's kind of what your asymptotes would look like. You don't have to graph them on this. This is called end behavior. End behavior. I do not care at all what is happening right here in the middle. Don't care. Don't look at it. We're looking at the end behavior. So as x gets bigger and bigger and bigger, y is doing what? Getting bigger and bigger and bigger, so we're going to infinity. And then as x gets smaller and smaller and smaller, y is getting smaller and smaller and smaller, and that's becoming negative infinity. Okay, does that make sense to you? We good? Mr. Reyes, are you with us? Okay. We good? All right, so now let's see. Now our answers are not always going to be infinities. Could be something else, and this is where our horizontal asymptotes come into play. Remember, your vertical asymptotes affect continuity. Your horizontal asymptotes can affect end behavior. So this says, as x moves towards positive infinity, x moves towards positive infinity and negative infinity, it's possible for f of x to be approaching a certain value instead of an infinity. So when I look at this, we'll draw in our asymptotes again. We've got one right here and one right here. Since my vertical asymptote is kind of in the middle, it's middle behavior, and we don't care about that. I care about the end behavior, and that's why this makes a difference. So this asymptote is stopping y from going to negative infinity, right? But as x gets bigger and bigger and bigger, y is going to get closer and closer to this asymptote. Does that make sense? So as x approaches infinity, f of x is going to approach negative 1. As x approaches negative infinity, what is y approaching? So as x approaches negative infinity, is this going to come up over this asymptote? No, so it's going to go negative 1. So both directions it's approaching negative 1. One is just from the top and one's from the bottom. Okay, we good? So let me ask you a question. Did you learn that you can never cross an asymptote? Were you taught that? Okay. So like this asymptote, because I'm approaching it, have you been told that you can't actually cross one? Because you can. Just want to make sure you know that. So on number 10, this is kind of a little side note here. Your asymptote is actually y equals 0. What this function is doing is it looks like this. So it actually crosses it, but then it comes back down. So I'm just kind of throwing that out there. So when we do this, as x approaches infinity, f of x, it goes up and then it's approaching that asymptote again at 0. And as x approaches negative infinity, y is also approaching 0. Okay. Does that make sense to you? We good on that? Okay. Number 11, we have an asymptote here and here. So as x approaches infinity, what does f of x approach? Negative 3. As x gets bigger and bigger and bigger, your y value is approaching this asymptote, which is at negative 3. And then as x approaches negative infinity, your y is coming up underneath this asymptote, and it's also approaching negative 3. Does that make sense? Okay. So then I have, on 12, I have an asymptote here and here. So y'all fill those two in. So as x approaches infinity, what does f of x approach? 2. And as x approaches negative infinity, f of x approaches 2. Okay, and these two numbers, see how they're the same each time? It's not necessarily always the case either. We'll get to that. All right, so let's look at number 13. So number 13, I'll tell you where the asymptotes are. They are here, and then here, and here. What is this topic called we're doing? What is it called? Well, it's continuity and what does it say? End behavior. So, do I care about what's going on in the middle? Not even a little bit. This could be anything here. Don't care. Doesn't matter how crazy it looks. I care about end behavior. As x approaches infinity, what is f of x approaching? Negative 2. And as x approaches negative infinity, f of x is approaching negative 2. Okay? So don't let the middle stuff, mess you up or confuse you. On 14, I have this asymptote here. This might be an asymptote. It might not. It might actually come to a point there. Does it really matter? No, because that's in the middle, and I don't care about that right now. I care about the end. So as x approaches infinity, f of x approaches what? 0. And as x approaches negative infinity, f of x approaches 0. One more. There's an asymptote here. There is no vertical asymptote. So, as x approaches infinity, what does f of x approach? I think it's negative 5, but that's okay. They're tiny, I know. Negative 5. In cases like that, let's say that this was a problem on a test or something, and you put negative 6, I probably wouldn't count it wrong because clearly you know what's going on, and the boxes are tiny. I get it. Then as x approaches negative infinity, what does f of x approach? Because it ain't negative 5. Positive infinity, exactly. As x gets smaller and smaller and smaller, y is getting bigger and bigger and bigger, and it's infinity. So like I said, they don't always have to match. It just depends on the graph. Ask me a question, Adrian, because I can tell by that look. You're like, what? Do I need to repeat it? Okay. Glad I could help. Everybody else good? We good? Awesome. So you got a little over 10 minutes left. Get started on your Delta Math. Delta Math, Delta Math.